Let's now introduce a new class of components called dependent sources or controlled sources. Up to now, we have seen only independent sources, that is, sources that have a voltage impressed or a current impressed that are a specific value that doesn't depend on anything in the circuit. Now, instead, the voltages and the current of dependent sources depends on another current or another voltage in the circuit. The new element that I'm introducing is the voltage-controlled voltage source. Is a voltage source, so the symbol is similar to the voltage generator, but this time the symbol is square instead of a round one. And the electromotive force, that we call E hat, is not independent, but depends on the voltage that is defined somewhere in the circuit. If the voltage is Vx, the electromotive force of the voltage control voltage source is alpha Vx. Alpha is a proportionality constant that is called voltage gain. The second element I'm introducing is the current controlled voltage source. So, the symbol is exactly the same as the previous one because it's a voltage source, but its electromotive force, E hat, is this time dependent on a current in the circuit. Let's call the proportionality constant R, Ix, because dimensionally this value is a resistance. The value R is called trans resistance because the value of this resistance transfer the value of Ix into the value of the electromotive force impressed by the generator. The third element I'm introducing this time is a current generator that is dependent on a voltage that is defined somewhere in the circuit. So this element is called voltage controlled current source. The impressed current, let's call this current A hat, is GVx, where G is the proportionality constant and is called transconductance. Finally, the last element is the current controlled current source, where the impressed current of the dependent current generator depends on a current that is defined somewhere in the circuit. And the proportionality constant beta is called current gain. So, with dependent generators, we have the quantities Vx and Ix that are called controlling variables. While the electromotive force of the voltage generator and the impressed current of the current generator are called controlled variables. Let's now see how we can deal with controlled sources in a circuit. Let's suppose, for example, that we have this circuit where we have a current generator whose current is dependent on the current Ix flowing through the resistance R1. So the current generator is a current controlled current generator. The method is based on multi-steps. The first step is to consider the control source as an independent source, at least for the moment, and to calculate the controlling variable. The first step is to consider the control generator temporarily as an independent source and calculate the controlling variable. In this case, we can apply the Millman's theorem to calculate the voltage V first, and then from the knowledge of the voltage V calculate Ix. The voltage V applying Millman's theorem is fraction line, the denominator is made by 1 over R1 plus 1 over R2. At the numerator we have two terms, one for each generator, E over R1 for the voltage generator, plus A hat for the current generator. We can go on with the algebra of this formula, having R1, R2 divided by R1 plus R2 that multiplies E over R1 plus alpha Ix. If we use the common denominator, we have fraction line R1 plus R2, R2E plus R1, R2 alpha Ix. Once we have the voltage V, we can apply Kirchhoff voltage law at this loop here. Let's consider, for example, the clockwise orientation. We have E plus R1 Ix minus V equals 0. So, we can identify Ix from the previous formula, that is V minus E divided by R1. Now we can substitute the value of V that we have found with the Millman's formula to obtain that Ix equals 1 over R1 that multiplies R2E plus R1 R2 alpha Ix divided by R1 plus R2 minus E. We can now apply the common denominator in the parentheses, so we have R1 plus R2. Let's first consider the term with alpha, so we have R1, R2 alpha Ix, and then for the term with the voltage generator E, we have R2E minus R1E minus R2E. So the only term that is left is minus R1E. We can then simplify 1 over R1 with the R1 that we have at the numerator. So, to conclude, this term is alpha R2 Ix minus E divided by R1 plus R2. The second step is to unwind the previous formula in order to calculate the controlling variable. In fact, here we can see that we have the controlling variable at the left-hand side but also at the right-hand side. So we can factor out the current Ix in order to have its value. So in this specific case, we can say that R1 plus R2 Ix equals alpha R2 Ix minus E. Now, let's move the terms with Ix at the left-hand side. So we have R1 plus R2 minus alpha R2 that multiplies Ix equals minus E. So we have alpha minus 1 R2 minus R1 Ix equals E, and so we can obtain Ix as E over the previous part in square brackets, alpha minus 1 R2 minus R1. Now that we have calculated the controlling variable, the control generator can be really considered as independent, and so we can calculate the unknown of our problem. In this particular exercise, we have to calculate I2, and so if we apply the Kirchhoff current law to this node, we can say that the current supplied by the current generator equals I2 plus Ix. And so I2 is A hat minus Ix. The value of A hat is alpha Ix minus Ix. So we can replace here the value of Ix with the value that we have found previously, and so we have that the current I2 equals alpha minus 1 divided by alpha minus 1 R2 minus R1 times the voltage E. And once you have the numbers, this value is completely defined. Let's see what happens if we have to calculate the Thevenin's or Norton's equivalent of a circuit where we have a dependent source. The first consideration is that we can only calculate this equivalent when the controlling variable is inside the circuit. So, like in this case, if we have the controlling variable inside the circuit where in this case, for example, we want to calculate the Thevenin's and Norton's equivalent of the circuit at its terminals A and B, and the controlling variable Vx is included in this two-terminal component. If this controlling variable is in another place of the circuit, maybe here, for example, to the part of the circuit that is connected to the circuit at the terminals A and B, the equivalent circuit with Norton's or Thevenin's two-terminal component is not possible. The first step is the calculation of the Thevenin's resistance or Norton's resistance. They are equal. Let's call these resistance R equivalent. So this first step is common to Norton's and Thevenin's equivalent circuit. The first consideration is that we can only switch off independent generators. By doing so, the circuit is no more passive. So it's not made only by resistors. And if we are in this condition, it's impossible to calculate the equivalent resistance by applying series and parallel connection or star to delta transformations in case we don't see any series or parallel connections. So the only possibility here is to calculate the equivalent resistance as the ratio between a voltage and a current. In the sense that if we have a circuit that is characterized by two terminals, if we want to know the equivalent characteristic at its terminal, so its constitutive equation, we can always apply a voltage generator, calculate a current supplied by this generator, take the ratio between the two, and get the equivalent resistance of this network. Or, Similarly to what we said before, we can apply a current generator with a known current, calculate the voltage, and then get the value of the equivalent resistance by applying the ratio between the voltage calculated and the current impressed by the current generator. If we switch off the current generator, that is the only independent generator of the circuit, we are in this condition, where we can calculate the equivalent resistance at AB terminals by applying a voltage generator and calculating the current, or a current generator and calculating the voltage. From the result point of view, it doesn't matter if you apply a voltage generator and you calculate the current, or vice versa. But from the calculation point of view, the fact of selecting a voltage generator as a source or a current generator as a source make a big difference, in the sense that sometimes applying one generator or the other simplifies the result. In this particular case, for example, if we apply a voltage generator here, let's call this VT as a test generator, and then we calculate the corresponding current, IT, the solution of this circuit is pretty simple, in the sense that we have a circuit with two voltage generators, but in this case the calculation of the controlling variable is pretty simple, because in this specific case it's easy to say that Vx equals the voltage of the test generator minus the voltage impressed by the control generator, or if you want, Vt minus alpha Vx. And so, in this specific case, the calculation of the controlling variable is trivial. So we have 1 plus alpha Vx equals Vt, and so the controlling variable Vx equals Vt over 1 plus alpha. So, if we have to calculate the equivalent resistance, we can calculate it by a ratio between the known voltage and the calculated current in this case. And we have chosen the voltage generator because in this way the calculation of the controlling variable is really simple. Now that the controlling variable is known, we can easily calculate the current IT applying superposition. If we switch off the dependent voltage generator and we keep the test generator on, we are in this condition where we want to calculate IT prime. And the value is pretty simple because we have two resistors connected in parallel, R1 in parallel with R2, that are connected at the terminals of a voltage generator. So IT prime is Vt over R1 parallel with R2. If we do some basic algebra, we get R1 plus R2 divided by R1 R2 Vt. If we switch off the test generator and we keep alive the dependent voltage generator, we are in this condition where we want to calculate the second contribution to the current IT. In this specific case, the resistance R1 is short-circuited, and the value of the current IT double prime is the voltage E of the voltage generator divided by the equivalent resistance at its terminals, R2. But note that this current is the current supplied by the generator. We want to know the current with the opposite direction, and so we need to put a minus sign. Or, in other words, we have minus alpha Vx divided by R2. If we remember the value of Vx that we have calculated in the previous step, we can easily write that the current IT double prime is minus alpha over 1 plus alpha R2 Vt. So also the value of the second contribution of the current IT is known, and in this specific case is no more dependent on the controlling variable, but we have expressed its value with the parameters of the circuit. We can now sum up the two contributions to get the current IT is IT prime plus IT double prime. IT prime is R1 plus R2 divided by R1 R2 Vt, and the second contribution is minus alpha divided by 1 plus alpha R2 Vt. We can calculate the common denominator, and we have fraction line 1 plus alpha R1 R2 at the denominator, and the numerator becomes 1 plus alpha R1 plus R2 minus R1 alpha that multiplies the voltage Vt. If we work with the numerator with basic algebra, we have R1 plus 1 plus alpha R2 divided 1 by 1 plus alpha R1 R2, and this coefficient multiplies Vt. So we can get the value of the equivalent resistance at the circuit terminals A and B by calculating the ratio between Vt and It. So what we wanted to know are equivalent is Vt over It, that in our case is 1 plus alpha R1 R2 divided by R1 plus 1 plus alpha R2. If we want to calculate the Thevenin's equivalent of this circuit, what we have to do is to calculate the voltage at AB terminals, this voltage here, and this circuit is nothing different from what we have seen before, so it's the calculation of a voltage across a resistance in a circuit where we have independent and dependent generators. So we have to apply the standard method. The first step is to apply superposition, assuming that the voltage generator is independent. And then we have to calculate the controlling variable. So what we want to do is to calculate the voltage Vx as the sum of two contributions. The first contribution is the contribution due to the voltage generator E. If we switch off the current generator, we have a circuit. If we switch off the current generator, we have this circuit where we want to calculate the first contribution to Vx. And this contribution is pretty simple because we just have to apply the voltage divider rule. So we have R2 divided by R1 plus R2 E with the negative sign because of the orientation of Vx. The second contribution due to the current generator is simple as well, because the voltage Vx is the voltage across the parallel of R1 and R2, and the total current that is flowing through this parallel is the current of the generator. Also in this case, the sign of this voltage is negative. Or if we want to express clearly the value of the voltage, we have R1, R2 divided by R1 plus R2, A. Finally, we can apply superposition and say that Vx equals the sum of the two contributions, Vx prime plus Vx double prime, or minus R2 divided by R1 plus R2 E plus R1A. The second step, so, is the substitution of E equals to alpha Vx into the previous equation to get Vx. So we have Vx equals minus R2 divided by R1 plus R2 alpha Vx plus R1A. If we move to the left-hand side the terms with Vx, we have 1 plus alpha R2 divided by R1 plus R2 Vx equals minus R1 R2 divided by R1 plus R2A. If we apply the common denominator, we can also simplify this denominator from the left hand side and the right hand side, and we have R1 plus 1 plus alpha R2 Vx equals minus R1 R2A. Or we have the final value of Vx as minus R1 R2 divided by R1 plus 1 plus alpha R2 A. And this is the value of the voltage Vx that is the controlling variable in our circuit with dependent generators. The third and last step is the calculation of the real unknown of the problem, because now that we have the controlling variable, also the dependent generator has an expression that is independent on the behavior of the circuit, but depends only on its parameters. So the last step is the calculation of VTH. So that we can easily write VTH as Vx plus E, or Vx plus alpha Vx, or 1 plus alpha Vx. If we substitute the value of Vx that we have calculated previously, we have minus 1 plus alpha R1 R2 divided by R1 plus 1 plus alpha R2 A. And this result must be coupled with the equivalent resistance R equivalent that we have found previously, 1 plus alpha R1 R2 divided by R1 plus 1 plus alpha R2. For curiosity, let's calculate the short circuit current that allows us to calculate the Thevenin's equivalent. Just for curiosity, let's also calculate the Norton's current. That is the current that flows in this circuit here when we short circuit the terminals A and B. The current IN. If we short circuit the A and B terminals, R1 is short circuited. And if it's short circuited and we apply the Kirchhoff voltage law to this loop here, we can write that Vx plus E equals 0. So Vx plus alpha Vx or 1 plus alpha Vx is 0. And this is true only if Vx equals 0. So if we short circuit the two terminals, we have found that the Vx is 0. And if Vx is 0 also E. So in this circuit, we have actually a behavior such that, so in this circuit, we can see that the current of the current generator flows through the short circuit. And so we can easily say that IN equals minus A. It's easy also to see that this result can be obtained if we take the ratio between VTH and R equivalent. That is the formula that allows us to transform the Thevenin's equivalent into its Norton's equivalent. So, by the analysis of this circuit, we have to remember these two conclusions that are conclusions that hold for every circuit with dependent sources. The first consideration is that we can calculate the Thevenin's or Norton's equivalent only if the controlling variable lies inside the circuit that we are considering. The second conclusion is that if we have to deal with circuit with dependent sources, the calculation of the Thevenin's equivalent or the calculation of the Norton's equivalent are not similar from the point of view of the calculation complexity. In this specific case, for example, the calculation of the short circuit current that is required by the Norton's equivalent is much more simple than the calculation of the open circuit voltage required for the Thevenin's equivalent. So, as a take-home message, we don't have to choose a priori if we want to calculate the open circuit voltage or the short circuit current, but we have to look at the circuit and try to understand if one way or the other is preferable from the complexity point of view.